nomenclature quiz on B2L will be due at 11:59 p.m. So by Wednesday night. And synthesis is up. It says for Wednesday, get the synthesis. Anytime you want to get it, start working, go ahead. The physical properties will be due next Monday. That's the March 4th already. Wow. And that's actually something you'll be turning that in as a piece of paper. Okay? And then the next Wednesday, which is the 6th, is the Ketones and Aldehydes quiz. Nomenclature quiz. And synthesis. Synthesis actually, honestly, you'll be able to do most of it by the end of this lecture, because you already know every way I'm going to talk to you about how to make a ketone or an aldehyde, you already know. We're not going to introduce you to anything that is new. Some of the larger molecules, though, you'll have an easier time making them after we've discussed reactions. But you could, after today's lecture, finish the whole synthesis. Just some of them might not be the prettiest thing you ever saw. Okay? So those are our due dates. And what we need to do now, it seems like we last lectured like 100 years ago, but we were in the middle, I think, of naming the ethers, the cyclic ethers. We were starting to fool around with those. Now, I know I gave you guys, I'm not sure exactly where we stopped, so I'm just going to pop these up again. You guys had 4-membered rings, and then we did 5, and then I gave you guys the name for the 6-membered ring. We'll deal with 3-membered rings on their own in just a second. But you guys should have the names for these things. And just their common names again. I don't even have them memorized. If you want to memorize them, you can use it out. Oxolane and oxane. Collectively, you can go oxa, cyclo, whatever it is. So this would be cyclobutane for 4 atoms. So oxacyclo, the number of atoms in the ring. That to me is the easiest thing to memorize. I think that's where we stopped. It's just presenting those. So what I'd like to do now is just do one quick example on what to do when there are substituents on there, how to deal with that, because I don't think we talked about that. So let's pick, I don't know, let's do this guy. And let's stick some groups on there. Let's put on OH and methyl. These are really pretty straightforward to name because the hetero atom, which is the oxygen in the ring, it is given number 1. So you take that ether ring as your parent. Even though the alcohol technically has higher priority, but this would be extremely difficult to name as an alcohol with a cyclo whatever it is, so people don't do that. They take the ether as the parent, and then we'll name these guys as substituents. And you don't even have to think because the oxygen is number 1. So the only choice you have is which way you're going to go. And guess what dictates that? Keeping numbers as small as possible, right? So what we're going to do is we'll be going that way. Okay, then you just line things up with their numbers alphabetically. So what do you want to call this? This is 1, so that's 2. There's 3, there's 4. 4 ethyl.
2
hydroxy. And then you can name this whatever you want. You could call it oxane. If you happen to have that memorized for the test, that's perfectly acceptable. If you're like me and you do not have that memorized, then you could do oxa, cyclohexane. And that would be fine too. That's what I do, because I don't want to bother memorizing the other stuff. Okay, so that's pretty straightforward. Yeah, exactly.
So we just understand that if we have the oxygen, that's why we understand that that's the first one.
Oxygen's always going to be the number 1 in the ring. Yep. Yeah.
You can't do hexane 2-ol just because it's like a ring, or?
You know, there's no efficient way. If you were to do it's not a hexane, you'd have to somehow deal with that ether being in the ring, which there's no way to do that really. So it's not at all a good way to name it. Okay, so we're kind of going to leave these behind because they exhibit a lot of the same properties as regular ethers in that they tend to be not very reactive, and so they're useful as solvents. And last time we had talked about this guy right here, in fact, being called oxalate if you wanted to, but it has a common name, tetrahydrofuran. You guys have probably seen, you know, under the arrows, when you're looking at reactions, they'll say whatever the reagent is, and then it says THF.
BH3.
Right? Yeah, BH3THF, exactly. This is THF. It's a solvent. It's an ether solvent. And so these cyclic ethers by themselves aren't very interesting because they don't do very much. They're only going to open up with hot, strong HI or HBr. Not very exciting. The one we're going to focus on today is the three-membered ring. We're going to go over that. Does everyone have this down? It's on the schedule, okay. Something tells me, I don't know if this is true, I should probably find out. If I work on that lower board, is that hard to see because of this bench?
No.
No?
He's
Okay.
getting up on the back, so.
All right. Yeah, I'll try to do that then. All right. The three-membered ring is actually kind of synthetically interesting. This has a couple names. This guy right here, epoxide, oxyrane, ethylene oxide. Those are kind of all of its aliases. And it's interesting because it's highly strained. And that means that it's fairly easy to open. So that makes it useful for synthetic things. Yes?
That's not the epoxy that we hear about with like glue and plastic and that kind of thing, is it? Or,
I don't think so. That's a polymer.
okay.
It might have this as a like a unit in it that will open up most likely. But I don't think so. I don't know what epoxy itself, what it looks like. I never thought to look. You know, Chris? Epoxy?
I think it's what you said, where if it's the monomer unit is an epoxide.
Yeah.
As a polymer.
But it's a polymer. I don't know what it looks like as a polymer.
No, it's not an epoxide.
Yeah. So this is the guy, we've already used it, and we used, I saw some of you guys on the exam, you were using it. It was used with Grignards, is how we've used it to pop it open and put two carbons in an alcohol. We're going to do a little more with it today. First, we got to figure out how to name it. We're going to learn how to put substituents on it, and synthetically, that is really, really useful. And we'll do a few synthesis problems. It makes your lives a lot easier than they were once you learn how to do that. First, we have to name them. So, there are two ways. And the choice really boils down to whichever's easiest. So, the first way is where the epoxy is taken as a substituent. Usually, that's done when there is something on it that is higher priority. So, as an example, say I had an alcohol, and here's my epoxide, and let's put a double bond on it. So, just looking at this molecule, the ethers are, if you look in your priority list, they're down in the subordinate group. And so this molecule should be named as an alcohol. And then the rest of the stuff is just substituents. The reason we didn't do that there is it was so difficult to deal with that side chain that went to an O. So they don't do that with those. But with this one, what we're going to do is we are going to treat this as a substituent. And the way they do it is they put both numbers that it's spanning. I don't know why they do both. If it does one, it has to do the other, whatever. So they put both numbers, and they call it an epoxy substituent. So, naming this thing, I have 1, 2, 3, 4, 5, 6. And so I am going to say 4, 5. They actually put both numbers. And I guess maybe that's so that you know that it's going this way, not that way. The only reason I picked for that. Then epoxy. And then it just names like normal. So this is 6 carbons. So it is going to be X 2 E 1 all. And I've got a little work to do to kind of tighten things up. Yes?
Could it be the second number, because if there's another chain coming out of 4, then there's nothing you can do. There's like a side chain
Yeah,
coming out of 4.
maybe. I'm not, it
But if-
seems, if I put 5, I guess you wouldn't know if it's starting at 5 going this way, or starting at 5 going that way. But if there was something else coming out here, I would just treat it as another substituent. Right? But the more I think about it, the more it probably just tells you which way you're going with that. I'm not quite done with this.
There's an E after the 2.
Yeah, there should be an E after the 2. And one thing you'll often see is you will see some stereochemistry associated with the epoxide. So here I've got a group coming up out of it, and here a group coming down. So often you'll see a trans or a cis out front, depending on how those groups are oriented. That's something if you leave that out, I'm not going to come unhinged. So. Okay, so that's the first way of doing it. The second way is where the epoxide is taken as the parent and the things coming off of it are substituents. This is really useful when there are alkyl groups coming off of it, so where you have something like this. And that out there somewhere is not a higher priority group. So an example for this one, let's do something like that. It would be perfectly acceptable to name this as an alkane with an epoxy substituent, just like we did over there. Totally okay. But you can also name it as, this is my parent, just like we did with this thing, and then just put the groups off of it. So this is number 1. And then I gotta decide which way to go. So I'm gonna have a 2, 3, regardless of what I do. You guys see that? No matter which way I go, it's 2, 3. So how am I gonna decide? Alphabetical, yeah. So if I go counterclockwise, then I get ethyl instead of isopropyl first. So we'll go like this. So this becomes 2 ethyl, 3 isopropyl, and then it is just oxyrate.
You can also say oxycyclopropane.
You could also do oxacyclopropane. That'd be okay too. That's very consistent with what we did earlier with the larger ones. And either one of these is acceptable. It really boils down to which is the easier one. Okay? Now, on your synthesis problems, we let you guys use just plain epoxy. And that's always been one of the choices. That's this guy right here. So it's a gas, it comes in a little bottle, and you bubble it through your reaction. And that's great for adding 2 carbons and no H2, which then you can do all kinds of things with. But you'll find on synthesis that it can be really useful to have your epoxide have substituent groups on it. So have one that's a lot more complicated. As an example, let's see if I can make one up out of my head real quick. let's just work our way backwards here by using this. Fennel Grignard, everyone knows how to do that. And then, looking at this, I would think, well, if I didn't know that I was going to do a Grignard and epoxide, I'd probably do some Frito Crafts thing, and then MDS, eliminate, and then something to put it out, right? You do all those things. There are about 4 or 5 steps you can do. But what I can do is I can do this.
Oh.
And I am done with the problem,
That's so cool.
right? The problem is done. Because all that's going to happen is this guy will attack right there, pop that open, and I'm done with this problem. So all I have to do is be able to make this. Okay? This is so much better than what you've been doing. And you'll see on the synthesis homeworks, I use it whenever I can. Because then I can put really complicated groups on them, just like poof, there they are, right? So it's great. So, to do this, I need to be able to build this, right? And it's fairly straightforward to do. So let's talk about synthesis of epoxides. There are 3 ways. One you really won't use. It's industrial, but every book puts it in, so we'll do it. This is not something that you would do in lab, but and all of these syntheses, by the way, come from double bonds. So with the industrial one, you would have something like, I don't know, let's take this guy. There's a double bond. So they all come from alkenes. And what they do typically is silver oxide, oxygen, and heat. And there's your epoxide. That's an expensive way to do it. They have ways of recovering the catalyst, right? And in lab, you're not going to run around and use silver like crazy. So this is not how it's done in lab. In lab, there are 2 ways. One of them is a variation of something you already know. So let's do that one first. Via a halohydrin. You guys remember a halohydrin reaction?
Yes.
Yeah, it sounds familiar?
Yeah.
Okay. So let's go ahead, let's do a halohydrin. Let's take that. I imagine you could build that, right?
Yeah.
Okay, so you build that. Yeah, it's nice, you're laughing, right? Which is good. Think about that very first homework set you were doing and how impossible that 3-step synthesis was, remember? And now you guys can build that pretty easily. So there it is. And with a halohydrin, Br2, H2O. So, you take the product, let's see. I always have to think about this. Bromine does bromonium. Water attacks the more substituted one. So we are going to end up with OH, Br. Okay, so far? That's the part you know, is the halohydrin. And now what you do is you take this product, and oftentimes you probably wouldn't even bother isolating it. You would just have your container stirring, let it go for an hour, whatever it is. Maybe monitor it by TLC, which is a pretty common trick. You actually take a little drop out of the reaction, do a TLC real quick, and the TLC of this will look very different than this. So you can watch this spot get smaller and smaller and smaller and disappear, and then this new spot appear. Okay, so as you're monitoring by TLC, decide you're done. Then you treat it with base. What happens when you treat it with base is you make a little bit, not much, but a small amount of the alkoxide ion. The pKa's for the OH and the OH minus, very similar. So it's not like you're going to get 100% deprotonation. You're going to get a little bit. So technically, we should go like that. But a little bit is okay because here's a nucleophile. Here's a leaving group right there. And we do an intramolecular SN2. And there you go. Yes?
Does it have to be cold to keep the bromine on there, or does it matter?
You know, it doesn't necessarily have to be, no. Okay. So that's one way of doing it, but it's probably not the most common way. In almost every organic lab, they have the reagents on the shelf to see. And there are a lot of variations of the two. I'm going to give you two reagents, and there are others given in different books and in the literature and things, lots and lots, but they all have the same trend. This is via something called a peroxy acid. So first let's define what a peroxy acid is. It's a carboxylic acid, but there's a peroxide involved in it. Hydrogen peroxide was HOOH, right? So a peroxy acid looks like that, a little bit weird. It's two oxygens. So it looks kind of like a peroxide. And what goes on with these is you take your alkene, again you have to start with an alkene, and you treat it with whatever your peroxy acid is going to be, and you end up making the epoxide. Now, as far as the kinds of peroxy acid, there are a couple of common choices. Probably the most common one, and the one that my lab had on the shelf, MCPBA. That's almost like having sodium hydroxide in your lab. This stuff stands for metachloro per benzoic acid, and it looks like this. There's the perbenzoic acid. Metachloro is right there. That's MCPBA. So what I would put here is MCPBA solvent, something inert. Methylene chloride is a real common one. And you get this epoxide. Another one that's given, it's not as common, but MMPP is another one. You might see there, chemists love all these little like short names like this. This stands for magnesium monoperoxy phthalate. And in case you're wondering, I'm going to make you give me the name of MMPP or those, I'm not. Okay, so you can, on a synthesis, really just write MCPBA over the arrow. That's okay. This looks like, I had to look up a picture of this guy. It's a benzene. There's your peroxy acid, and it's a carboxylic acid. There's two of them with a magnesium 2+. So it's actually a salt. It's a salt peroxy acid. But you see again, the important thing is that unit right there, the peroxy acid part. Now, as far as how it works, I'm going to try the mechanism. I get it right about half the time. So let's see how I do it. It's kind of a cool mechanism if you get it right. All right, let's try this. Then I want to do, I want to line this up. might get it right. Ready? Here we go. So this comes down. This comes up. There's where your oxygen has just come in. Okay, just suck the oxygen out there. This comes over. So far, so good? Okay. That goes on to the oxygen. Now here's the fun part. There's little hairs here, right? They grab the hydrogen.
It's like a complicated half-bridge and feels that
And it all happens at the same time. It's this big concerted thing. I will not test you on this. It's just kind of fun. So, looking at this nightmarish mess, what we have is the part we care about, which is this. Okay? The rest of the molecule goes away as, let's do some bookkeeping here, this is gone. Okay? This became a C double bond O. Right here, that's a C double bond O. This became a single bond to an OH. So this looks like this. R, C, double bond O, OH. It goes away as a carboxylic acid. We just sucked the peroxy part of it out. This is one of the most interesting mechanisms, I think. So, now, it's going back to our little plot we were doing where we saw how easy it would be if you could build that. I think it was, wasn't it that guy right there? What you do now is break it right there. What I need is MGBR, that's easy, and I need this.
You know, turn that methyl into an ethyl.
Turn the methyl, oh, this one?
Yeah. There we go.
So I need that. Which means what I really need is that. If I can build that alkene, then I can build that epoxide, and then I can make that molecule in one reaction. Okay, and this shouldn't be too hard from Grignard's and an elimination with H2SO4. That's how you do something like that. Okay, so really, it just boils down, if you see to do this, it boils down to just building an alkene. Okay, the trick is really seeing that you can use it. And what I would do is from here on out, anytime you see that you've got a fairly complicated molecule, maybe even on both sides, and there is an alcohol, or let's say maybe even a ketone that came from an alcohol in the center, start to see if you could have done an epoxide in a Grignard somewhere. And it can really save you some steps. Okay, questions on that? All right. So let's go ahead and look at ring opening of epoxides. When you have a substituted epoxide, so in other words, the sides are different. Say you had something like this. Like that. It matters which side you're opening the epoxide on. You could have a tap here, and that would give you a different product than a tap here. They would give you two different things. And so you have to be able to predict, well, when I add a Grignard reagent, for example, is it going to attack at A, or is it going to attack at B? Because it matters. If you want to attack at B, but it attacks at A, you're going to get totally the wrong product. Okay? So, let's go ahead and look first at ring opening with nucleophiles, which would be things like Grignard's, alkylithiums. OR minus, another nucleophile, OH minus. Any kind of decent nucleophile can open these. The thing that drives attack with nucleophiles is sterics. So it's pretty easy to predict where you're going to get attacked. What that says, if I had, let's say I had, what's a good alkyl lithium? I don't know. Let's say propylithium. 1, 2, 3. This is minus Li plus. So this is this. Propylithium. And I want to attack this guy. I add that to it. There are two places it could attack, here or here. And in terms of the delta plus on the carbon, they're both essentially equal. The oxygen isn't really pulling any more from that side than that side. What's going to drive this guy is where it's easier to get in. And they are going to attack the least hindered carbon. So, I'm going to have the alkyl group attack right there. And it will pop the ring open this way. So my product will be C, and then this came from the alkyl lithium. Then it will be, let's go to a different color. The carbon of the epoxide, that's my first carbon there. Then the second carbon, which has the branches on it, and an OH. Assuming I've added H3O plus. Okay, so take a look at that, make sure it makes sense. Yeah,
No.
no, okay. Okay? Any questions about that? Okay, yeah.
That says H3O plus, right?
It says H3O plus, okay, because otherwise it'd just be O minus. Now, what's a little different is if you ring open this in the presence of an acid. So, let's do one more example. Probably the best way to introduce this. Let's do a ring opening with that guy, OR minus. First is a nucleophile, just a straight up nucleophile. Then I'm going to do it as an alcohol in the presence of acid, and we'll see the difference. So, example number 2. Let's take that, and I am going to treat it with let's just use a oxide. So there's a oxide, H3O plus. So it's just a nucleophile. So it will attack the least hindered position, which would be this one. We will open up. And my product will look like this. I'll have OH on this first carbon, I'll put cyclohexane. And then attached to that second carbon will be OCC. Okay? That's just another illustration of just a plain nucleophile attacking. Now, let's look at case B. This is ring opening in the presence of H plus. So this would be acid catalyzed. Now doing this, you've kind of limited what you can open the ring with. I can't, for example, take a Grignard reagent and put it in the presence of an acid to open the ring, right? There's a fundamental problem with that, and that's the minute I put the Grignard in with the acid, they're going to react, right? So this is not even applicable for Grignard Grignards, for alkylithiums, anything like that. Where you're going to see this is you're going to see it with H2O, H plus, and alcohols, H plus. Something that in the presence of acid is going to be immediately destroyed. We won't see alkylithiums doing this or Grignards. Okay, so let's do it with the alcohol. And I'm going to show you the different result that you get. So let's do this guy. Same epoxide. Right there. Only this time I'm going to do ethanol with an H plus catalyst. The mechanism is slightly different. The first thing that happens is that the epoxide gets protonated. And that helps it open up a little bit easier. The reason I have to do that is that over here, the epoxide ring string, this is true, it will pop open. I have a superb nucleophile, right? A Grignard is a great nucleophile. These guys, OR minus, OH minus, they're really good nucleophiles. So they're good enough to pop open the ring. So there's not even an issue with them. Over here though, I'm throwing ethanol at the ring. It's not good enough. And so you've got to do something ahead of time to get that ring a little bit more active. And so what you end up doing is you form OH plus, and now the epoxide will open more easily. It'll open in the presence of what is a core nucleophile. So now I have to attack. And this is where the difference comes in. This oxygen now is electron poor. So it's pulling electrons away from the carbons pretty substantially. So the carbons develop delta pluses. So this carbon here and this carbon here have delta pluses. This is very much like the bromonium discussion we had. And remember the redoxymercuration? That one? Okay, same kind of discussion. So these both have delta pluses. The delta plus that's larger is on the carbon that is more substituted because it can stabilize it better. So that's the one that's important. The larger delta plus is right there at the more substituted carbon. That's what the nucleophile is going to attack. So let's get kind of cluttered. Let's go over here. I'm going to redraw that without letting jump on it. So we're going to get attacked at the carbon with the larger delta plus, which is the more substituted carbon. What are we using? Ethanol, right? So the ethanol attacks right there. And I forgot the key part. There we go. The ring pops open. I have OH. Here's my ethanol with the plus. And an OH sitting there. Then I have to get rid of that H plus. So I have some kind of base in there. Probably HSO4 minus would be my guess from our H plus catalyst. And it deprotonates, and you are left with that.
Professor,
Mm-hmm.
if you're gonna write out the whole reaction, how would you do it if you're just like?
If you're just writing out the reaction with no mechanism?
Yeah, like just cause like I don't know where you wanna put in the H2SO4, like in.
Oh, what you would do if you're just writing this thing out, it would just look like this. And you'd probably put catalyst right there,
That's all.
and that's all, and then you would just, show kind of right how it works. You show that, that's it. That's all you gotta do. So the take-home lesson is, with really good nucleophiles, for you guys, that'll be Grignards, alkyl lithiums for the most part, they'll attack the least hindered side. If you have acid, it's acid catalyzed, which you're really only going to see when the nucleophile is water or alcohol. If the nucleophile will attack the more hindered side. It's just not as common though. Okay? Questions? All right. Now the next topic before we leave ethers is more of a lab topic actually. It's worth talking about because some of you guys will be doing some summer internships and some of you will inevitably run into these. So we're going to spend a few minutes talking about crown ethers. Crown ethers are large, cyclic polyethers. They look like this. This is an example of one. And they're called crown ethers because when you look at like a molecular model of them sideways, they sort of look kind of like that when they get big, like a crown. Okay, it's down here. So that's why they're called crown ethers. They come in different sizes. So this particular one happens to be called 12 crown 4. And the way they're named is the 4 is the number of oxygen atoms, and the 12 is the number of total atoms. So that's 12 crown 4. Other common ones, 15 crown 5, 18 crown 6. They're just bigger. So 18 crown 6 is pretty big. What crown ethers are used for is a way to trap metal ions. They have in the center of them a pocket. There's empty space there in the center. And these oxygens have lone pairs. And so I can take a metal, M+, whatever it is, and if it gets in that pocket surrounded by this crown ether, there's interaction with the oxygen lone pair, it essentially gets trapped in there. So it's a way of removing metals that might be causing you trouble when they're attached to something else. The 12 crown 4 has a pocket that is sized for, in general, lithium. It's kind of small. So it's really useful for getting rid of Li+. Little bigger pocket of 15 crown 5 sodium, going down the table, right? And then the bigger one, potassium. There are all sorts of designer ones too that labs have built with different size pockets specific for certain metals, but these are the most common ones. Now, an example of where it can help you. I used in my research, I was doing a reaction that I had a starting material that took me about a month to make. It was tedious. And it looked like this. That was my starting material, and it just took a long time to make. And then I would treat it, and I would deprotonate here, and then turned out these hydrogens. somewhat acidic, not tremendously, but somewhat, so I could deprotonate them as well. So I actually made a dianion, which is hard to do. So to do it, I used the base I talked about a lot, tert-butyl lithium. Okay, that's the one that, when it was a THF, that catches on fire in the air from the moisture. Okay. So I would use tert-butyl lithium, and I would make this. The nitrogen would have a minus. I'd pull a hydrogen off on the other side, that'd have a minus. And the counter ion was a Li+. And that worked fine. There was no problem with that. And then my job was to add electrophiles to this. So I'd add whatever electrophile I was told to, electrophile of the day. And the carbon was more nucleophilic. So it went in and attacked the electrophile. And when all was said and done, this is the sum total of my graduate school career was that. I add electrophiles. And then the theory was if I added the right ones, this would act somewhat like penicillin, so it'd get shipped off and tested. There it was. So the problem with this was, this stuff took a month to make, and you couldn't scale the reaction up. The most I could ever run was like 0.5 gram, or it failed. And the popping yield on this, the best I could do was 10%. That's why when you guys come up and say, I got 60%, is that bad? I kind of laugh. No, it's okay. 10% was a great day, which was not okay, because this stuff took too long to make 10%. So we tried all kinds of things, the usual temperature, time, blah, blah, blah. None of it helped. So then, the theory was, well, maybe lithium is just too tightly complex to that. And it's hanging on, and the carbon's not as free as it could be. So let's get the lithium out of there. And so what I did is I just added 12 gram bar. It's a solid, and you literally go weigh out what you need, throw it in, it dissolves, and you run the exact same reaction. And when I did, the yield went up to about 30%, which seems still terrible. I was ecstatic. And that's as good as it ever got. But it was substantial, you know, it tripled my yield, adding the 12 gram 4. So that's the kind of thing those are useful for. And some of you guys this summer, if you do research, you'll probably run into these, or at least talk to someone who's using them.
If you used like sodium instead and 15 crown 5, would it change anything? Or do you think
You know, the base is such that sodium wouldn't make it. I needed a really, really strong base, so I was limited to tert-butyl lithium, which stuck me with a lithium ion. But it may have, you know, I don't know, if I could have found the right base. But I was stuck by that. Okay? Questions on ethers? All right, and we are done with ethers. We're going to go into ketones and aldehydes now. You'll find, I think, that synthetically they're quite a bit more useful. First thing, I want one of these in my house. This is awesome.
It's
Good night,
actually
kids.
I feel so powerful. Okay, nomenclature is easy, synthesis is easy. I'm going to turn the lights down just a little bit. This is on, the rules are on D2L, if you haven't got this yet. So what you can do is just copy down the molecule and its name, and then you can get the rules later, push you right past it. Okay, you guys can all see that? Okay, so we'll do aldehydes first. You're going to do the standard thing, find the carbon that is in the aldehyde functional group, and the longest chain, assuming there's just an aldehyde there, needs to contain that aldehyde. So we are going to be going, starting there, and we'll just find the longest chain that includes that carbon right there. So that's just going to be there. The aldehyde, I love naming these because they're brainless. The aldehyde carbon is number 1. You don't have to think. You don't have to sit there and look and count from the different sides. It is number 1. And so that dictates the numbering of your whole chain. You don't have to think at all. Then we're going to do the standard. You list your substituents alphabetically with a number. The parent is pretty easy. What are we looking at carbon-wise here? We have 1, 2, 3, 4, 5, 6, 7. So it's heptane is the alkane parent. You drop the E of the alkane and add Al, heptanal. Okay? So this one has a bromo at 3, methyl at 4, hydroxy at 6. And so, 3 bromo, 6 hydroxy, 4 methyl, heptanal. Huh?
I'm just a little confused by like hydroxy naming. You have like other things that I guess take precedence because like in other namings you use you like say heptan 6-all. So why are you not doing that now?
The only place that we did the something dash like for all, that kind of thing, was with alkenes and alkynes.
Okay.
And I think the reason we did that is because that alkene or that alkyne became part of the parent stem.
Okay.
We didn't have a situation where we could take the double bond and make it a substituent out front. It became actually part of the name, so we had to incorporate the alcohol and the alkene at the end.
All right.
But these others, this is an aldehyde, and so the hydroxy is relegated to a substituent. The only time you'll see that dash and all with other groups is alkenes and alkynes. Okay? Questions on that? All right. Notice that the number 1 isn't necessary because it has to be number 1. So you don't have to play. Okay, try your hand back. Some of you are probably debating on this one already, straight out of the chute. You have a couple ways you can go. You have to start right there, right at the aldehyde. So you could go across, then you hit this point here. And if you go this way, it's 2 carbons long, right? If you go up, it's 3. So this oftentimes causes confusion. The rule of thumb with IUPAC is you get the longest chain containing the most functional groups, which says that might not be the longest chain, right? Your parent is going to be right there. Even though it's not the longest chain, it gets that double bond. It has the most functional groups. And that really simplifies your naming quite a bit. All right, so be able to touch the stuff. What is that, Tori? A double bond, right? Okay. All right, so we decided this is the parent. What is this thing going to be called?
1,2-dimethyl.
Okay, I could call it 1,2-dimethylprobal. And I'm sure some of you guys call it something else. I could try, like 3-methyl isobutyl. You don't want to do that because what you're doing there is you're combining common and IUPAC in the same name. You stick with one or the other, but don't combine the two. the new way. 1, 2, 3, 4. Be 3-methyl. Butan. 2-enyl. Anybody do that? Yeah, okay. There's a few of you making the conversion to the dark side, but there it is. I still am not used to it, I don't know. So, either one's okay. Either one's fine. If you do this one, this whole thing's going to be parentheses, right? So if you do the top one, we'll alphabetize by D because we'll be in parentheses. If you do the bottom one, you're going to be alphabetizing by M. It just might affect where things go. All right, so the name of this guy, I think I did old school. I did 3-chloro, 4, parentheses, 1,2-dimethylpropyl, X, 4-E-ene-al. And notice that, once again, kind of like what Gabe was asking, with an alkene or an alkyne, that gets sucked into the parent name. It's never listed out front. Now for the fun. This is craziness. Here it is on a ring. Rings cause trouble. It's okay if it's benzene, because then it's just benzaldehyde. But if it's on a cycloalkane, that kind of loses their mind. And we'll see this with carboxylic acids, amides. It's just terrible. You have to just memorize it. When it's on a ring, here the parent is a cycloalkane carbaldehyde. I don't know. I didn't do it. There it is. So this thing is cyclohexane carbaldehyde is the parent. All right, so just memorize it. And the numbering, there's the cyclohexane carbaldehyde. The numbering is that number 1 is where the aldehyde is attached. So you don't start numbering on the aldehyde carbon, just the point of attachment of the aldehyde. Yeah?
That only applies if the aldehyde is directly on the ring.
If it's directly on the ring, right. Has to be directly on the
So
cycloalkane.
what if it was like there were 2 or 3 carbons between?
Okay, if it was, Ryan's asking, what if it was separated from the ring by 2 or 3 carbons? Actually, that's a lot easier. You're hoping that's what happens because, let's say it was like this. Like that, okay? This then becomes the parent, and it's a cyclohexyl substituent.
And even with all the different substituents on it?
Even because this guy takes priority. Even with all the other substituents. So if you had things on here, like that, assuming that your aldehyde's higher priority than these things, this is still your parent, and then you have this mess in parentheses. Okay, so you have all this in parentheses. So this only applies when it's directly on. Okay, so this guy's name is 5-amino 3,3-dimethyl cyclohexane carbaldehyde. And the reason I went that way is just to keep the numbering small. There's your number 1. And I would go 3,3 versus a 5,5. It was better. Okay? Now for ketones. Ketones are pretty easy. You have to think a little bit harder about the numbering, that's about it. So you're going to pick the longest chain that has the ketone carbon in it. And then if there are other functional groups, the longest chain with the most functional groups in it. And you're assuming that the ketone's highest priority, you have to give that carbon the lowest number. So you are going to have to think a little bit harder. And usual thing, deal with substituents along with their numbers alphabetically. The parent ending, it's a ketone, so we're going to call it an alkanone. So if it's hexane is the parent, 6 carbons, hexanone. The only wrinkle is that I have to give a number to the own part. I have to tell you what carbon it's on. So, looking at this guy right here, my parent will be this long chain. 1, 2, 3, 4, 5, 6, 7 carbons long. So it's going to be a heptanone as the parent. And the ketone gets what number?
Two.
Number 2. Yes, there's 2. So I'll be going here. And I'm going to have this enone thing I'm going to have to deal with. So, I'm going to have to write it. I can't stand it. What's the BR at? 1, 2, 3, 4, 5 bromo. There's methyl at 4. Okay, what do we do now? Kept, okay. How am I going to deal with that alkene? Not 2. Not 4. 3. Yeah. There's 1, 2. It starts at number 3. So we'll do kept dash 3 E ene 2 O. Okay, but yeah, right.
So that would be damaged if you had both the ketone and the aldehyde.
We're going to do one of those in just a second. So hold on. Okay, let's do one in a ring now. There's nothing weird about this. They don't have any funky name for it or anything like that. When it's in a ring,
That's 10 minutes.
10 minutes? Okay, we'll finish this one. And then we'll go. I'll do the next. When it's in a ring, something like that, this is carbon number 1, and this whole thing would be a cyclopentanone. So there's no weird, strange name for it. So that guy right there, there's number 1, and I'm going to go around to encompass the double bond. I want to give that double bond the lowest number. It's part of the parent name, and it's a functional group, so it gets priority over methyl. So it's 4-methyl cyclopent 2-ene only. I didn't need the number for the ketone because it is assumed to be number 1 in the ring. It's much like an alcohol on a cyclic compound. Yes?
I obviously don't have to mention it's E or Z.
No E or Z in a ring this size. The only time you have E or Z is when your rings get really big and could accommodate a trans bond. Yeah.
Will we ever have the case where we have a cyclic ether with a ketone or aldehyde?
Like directly on it. Yes, there is that case. It would be something like, is this what you're talking about, Ben, if you had something like that? Ugh.
What would take precedence?
Oh, the ketone would. I don't know what you call that. I'm gonna look it up. You know,
In the middle.
the ketone has priority, but I'm inclined to do the last thing we're gonna talk about. I'll be really fast. It's easier, really, to name it as a substituent. It'd be easy. I don't know if it's right though. I feel like that's what I want to do, but it could be wrong. I'll look it up. But if you're stuck in an aldehyde or a ketone as a substituent, the aldehyde group is a formal group, and the ketone is an oxo group. Yeah.
It says in the prioritization of functional groups that esters.
Oh, an ester, that's a lactone, and that would look a little different. It would look like this, like that. That's an ester because I have this unit here. That's different. So that's actually a ketone and a ketone. Those are called lactones, and we'll never learn that name, but we'll see. So here's an example, and then I'll stop. That's how your test. I have an aldehyde and I have a ketone. Who wins? Aldehyde wins. So this ketone is now a substituent. It's an oxo substituent. So this is 3-isopropyl, 4-oxo-hexanal.
So why don't you do the aldehyde and ketone like as part of the name, just like the enols or?
Oh, as far as like going hexan, al, 1, 2, 3, 5 own, like that, please don't. carboxylic acid, which you don't know how to name, but this is an example where this group, this aldehyde hanging off, is a formula right there. Okay, you won't have to name those because aldehydes is as far as we've gone so far. All right, the moment you've all been waiting for.